Have you ever wondered how your phone can pick out just your voice in a noisy cafe? Or how a simple watch can track your heartbeat with incredible accuracy? Well, behind almost all of that modern magic is something called signals and systems. It's kind of like the invisible language of our world, and it lets us build all the smart tech we use every single day. So, let's dive in and see how it all works. Take a look at this. This isn't just some random squiggle on a screen. It's a heartbeat, a signal that carries literally life or death information. But signals are everywhere, in radio waves, in your Wi-Fi, in the sound of my voice. And the biggest challenge for any engineer is this. How do you cut through all the real-world static and noise to find that one crucial message you're looking for? So here's our plan for today. We're going to start with the absolute basics. What even are signals and systems? Then we'll map out what the learning journey looks like. After that, we'll check out the super powerful tools engineers use, see how it all applies to real-life problems, and finally touch on what it takes to really succeed. We're going to break it all down step by step. All right, first things first. What are we actually talking about here? Before we can get into the cool stuff, we've got to understand the two main players in this whole story. Signals, and of course, systems. At its core, this is a really simple idea. A signal is basically just a way to carry information. Think of it like the sound waves traveling from my mouth to a microphone. And a system? Well, that's the thing that does something to the signal, like an amplifier that takes my voice and makes it louder. So one carries the message, the other one processes it. Simple as that. And this right here, this is the fundamental idea behind everything. Signals have the raw information. Systems are what we design to do something useful with that information. And math is the incredible language that lets us analyze, model, and build the whole thing. This simple relationship is the foundation of the entire field. Okay, so you get the basic definitions, but how do you go from knowing what they are to actually mastering this stuff? Well, let's map out what that journey looks like. This whole journey is laid out in 3 really clear phases. Phase 1 is all about getting the fundamentals down, learning the basic language of signals, and figuring out how systems work. Then, Phase 2 is where the magic really starts to happen, transformation. This is where you learn to see signals in a completely new way, in the frequency domain. And finally, in Phase 3, you take everything you've learned and apply it to solve real-world problems with messy, unpredictable data. So to put it another way, the whole process is super logical. First, you understand the language. Then, you analyze how systems react. Next, you learn how to transform signals to see what's hidden inside. And finally, you apply all that knowledge to go tackle some actual engineering challenges. It's a clear path from theory to making a real impact. And this brings us to the tools you get to use. And I'm not just talking about boring old equations. Think of these tools as giving you a kind of superpower, like X-ray vision for data. This quote just nails it. A tool like the Fourier transform lets you take a really complex signal, say a piece of music, and see every single individual note that makes it up. It's like going from hearing the whole symphony to suddenly seeing the sheet music for every single instrument. It lets you find the noise, spot the important patterns, and really see what's going on underneath the surface. And that's the perfect lead-in to what, for me, is the most exciting part. Putting these new superpowers to the test on actual real-world problems. Okay, check this out. This is where the rubber really meets the road. On the left, you see a perfect, clean signal, just like you'd find in a textbook. But on the right, that's the same signal, a breathing measurement actually, as it looks in the real world. Messy, noisy, and totally corrupted. The important information is still in there somewhere, but man, it is buried. And that is your mission. You get to use all these tools to model the messy situation, analyze what's going on, and then design a system to filter out all that junk and pull out the clean, original signal. This isn't just a classroom exercise. This is what engineers do every single day. And this whole problem-solving process is very structured. You don't just jump in. You start by modeling the clean signal. Then you actually add real-world noise to it. You analyze the system, use your frequency tools to see what's what. Design a filter to clean it up, and then, this is the most important part, you test your solution on a real messy dataset to see if it actually worked. And the best part, your playground for this mission is just incredible. You'll be working with real datasets from some of the most cutting-edge fields out there. We're talking about cleaning up ECG heart signals, decoding transmissions from IoT devices, or stabilizing a motor controller. This is theory with a direct line to the industries of today and tomorrow. So with all this cool, hands-on work, you're probably wondering, okay, how is all this graded? Well, the whole evaluation is really designed to support you every step of the way. The big emphasis is on continuous learning. 60% of your grade actually comes from coursework that's spread out through the semester, and the final exam makes up the other 40%. So it's a structure that really rewards consistent effort over time. And that coursework is split up really evenly. You've got 2 tests to check your understanding of the main ideas, and then that big problem-based learning project we just talked about, well, it carries the exact same weight. It's a really balanced approach that values knowing the theory and being able to actually apply it. It all really comes back to this one idea. For you to learn continuously, perform consistently, and ultimately to succeed confidently, knowing you have this powerful new toolkit at your disposal. So I'll just leave you with this final thought. Signals are carrying the data of our entire world, from the deepest oceans to the farthest reaches of space. The real question is, once you have the tools to see what's hidden inside all that data, what new discoveries will you be the first to unlock?